Today we have a talk, Debug for Bug, Crack and Hack Apple Core by itself. So I'd like to introduce Liang Wu and Moony Lee. If everybody could give them a round of applause. Thank you.
There are so many people. Let's the last topic, debug for bug, crack and Apple Core by itself. Let me introduce myself. I'm Lilang. I have 4 years security experience and mainly focus on macOS and iOS vulnerabilities and malware. I'm now responsible for the fuzzing project in our team. And this is Moony.
Glad to meet you, everyone. I have about 9 years security experience, and in the past years, I'm most on the macOS and Windows sandbox development, and now I'm focusing on the zero-day and exploit on the mobile-related bug hunt and exploit. And this is my conference list. Thank you.
This is the agenda of our topic. First, I will introduce the overview of kernel debugger in macOS, and then introduce our lldb fuzzer tool. After that, we will detail two kinds of hidden attack service on graphic drivers and how to fuzz them, and then give the demo video. Then we will show the bugs we have found. What's more, in order to apply the lldb fuzzer for hacking to SSH, we introduce a method to implement a kernel debugger based on open source networking drivers. Finally, we will give the conclusion. First, we will introduce the overview of kernel debugger. We can use KDP protocol to debug a remote device. This can be activated by modifying the boot args using AVRAM. And only a single debug can be activated at a given time. macOS has implemented different kinds of debugging with kernel, including Ethernet debugging, firewall debugging, and serial debugging. Actually, fireware and serial debugging are only act as a local proxy for the target machine. lldb still performs network-based debugging. This is an overview of kernel debugging. It mainly contains 3 parts. Ethernet driver responsible for implement receive packet and set packet and other essential functions. BSD kernel part responsible for using KDB pool and KDB replay handler to process debugger message. And networking family kernel extension is responsible for bridge these 2 paths. For the kernel part, when kernel bootstrap system will create a KDP init thread and implement a debugger trap. The KDP init thread will impose a KDP register function which can be used by our networking extension to register send and receive handler. The debugger loop within the trap is responsible for pulling and replaying the incoming debug message for after capture the exception. When Ethernet extension implements the RKDP protocol, KDP register function will register the receive and send handler into the debugger loop. After that, the debugger can be worked. What's more, XML implement all the debugger commands function in kdb.c field and register them into a dispatch table. And these functions make up the debugger work. In the Ethernet extension part, as mentioned, it must implement a pair of handler functions that are called to handle KDP transmit and receive requests during a debugging session. After you enable the remote debugger, it will call the attached debugger client method to init the KDP protocol, and use KDP register send and receive function, which is posted in BSD to register send and receive handler. And eventually, the debugger loop can connect the debugger world with the remote client. This is the UDP package flow, which indicates lldb world receive debug message and send the replace through Ethernet extension. Here is the toolset get from KDK, in mainly including API wrappers for basic lldb scripting bridge APIs and the implementation for all the debug commands. Now, let Moony introduce our idea about lldb fuzzer.
Okay. This is the whole architecture of our lldb fuzzer towards the macOS kernel debug, which is based on the lldb debug mechanism. As we can see, the lldb fuzz is based on the built-in debug mechanism of macOS, which intercept and break the execution of key APIs such as the lconnect call method and syzkaller as the key point. And fuzz corresponding data or code in the execution context. Since the most data or code dependency are kept during fuzzing, the fuzz activity could touch deeper code branches than the, for example, the typical syzkaller AFL-like method in our practice. And since we do not design the execution channel of fuzzing, the hidden attack interface would be exposed because of our deep interception. So we have more chance to find the hidden attack interface. Okay, this figure shows the architecture of lldb fuzz solution. The fuzz solution contains two kinds of parts. The left part is the remote machine or the host machine. And the other part is the target machine, which run our debug fuzzer. So as we can see that, we should pay attention that the main fuzz logic in the host machine, including the probe setup, mutation, executor, or crash monitor, are all implemented as a Python script based on the lldb framework. So the script could be actually executed in the target machine in the left part. So as the main module, we can see that the probe setup module will query the fuzz strategy, which contains also attack surfaces we collected from the, for example, the XNU kernel or the target kernel extension and the set, and pass them for the executor to deploy our probe point to target machine. When the target point is hit based on the debug mechanism of lldb, the control execution is transferred to the executor. And as our fuzz strategy, we will try to mutate or taint the input buffer from the user mode so as to cause the target kernel module to crash in the later execution. Actually, there exists kind of mutation strategy, as you can see, such as the random bit flip, integer increment or decrement, or something like that. And we also could control the mutation frequency and the scope to avoid the whole kernel system of system harm to keep the kernel fuzzing always active. And the other module is the crash monitor. It will monitor the status of the target machine based on the lldb command. Typically, it will send the call dump and the panic log to the remote machine or the host machine for further reproduction. And always we will reboot the target machine based on the lldb command if we have collected the scenario. As to catch the system crash at the root cause point, we have introduced the synchronizer mechanism in the right part of the target machine. The target machine will load our customized XNU kernel, which is open sourced, which will be compiled with the security features of kernel address synchronizer and memory address synchronizer. And this kind of topic we have introduced in our last year conference. As we can see, the normal macOS system has no Ethernet point, so as not to be enabled to be debugged. So remote debugger component in the target machine is customized network driver, which is enabled to set up to support remote lldb debug. We will introduce this kind of key module, how to implement this kind of remote debugger in the later part. And you can see that the XNU and the kernel extension is our fuzzing target for debug and for Fuzz. Typically, this kind of kernel extension could include some buggy modules such as graphic related or the audio video or the other kind of related driver. And this part is for the probe setup module. This module is for the probe setup configuration. Typically, we will set up a probe point according to you can see that the API name or the virtual address, which we are interested in, such as the lconnect call method or system call, which is the common attack interface for the kernel of macOS. And also we will configuration the condition strategy for the probe as the fuzz, for example, the fuzz frequency or the fuzz scope to avoid the system harm. The other part is the fuzz executor. This part is just to intercept the fuzz probe and capture the input buffer, and read the input buffer and mutate and write them to the kernel memory. You can see that this is the main control logic of our fuzzing strategy. And also, after the mutation, it will continue to give the exception to the left of kernel. And if crashed, he will call the crash monitor module to try to get the call dump and the other kind of logs for reproduction to the Fuzz server. And also, it will restart for the other session of Fuzz. And for the Fuzz mutation part, the main purpose is to try to fuzz or taint the input buffer, which is always valid from the user mode. And we have a chance to flip some content of the input buffer and keep the most of the other part is valid, so as to bypass the basic check of the in the kernel. So we have more chance to go deeper to the kernel or the driver part. And there are also many kinds of fast strategies, such as random int, increment, and decrement, and so that. And this is for the basic mutation strategy, such as control the fast scope by the percentage, or control the fast scope by the bytes. And the other part is the credit monitor. The credit monitor module is separated independently from the target machine to monitor the targeted kernel. And the main focus, the main target is to try to get the crash scenario, including the panic, also panic log and the call dump for further reproduction. And the other important part is the data generation for target machine. As we can see that lldb debug belongs to the passive fuzz. So in order to touch the more depth attack interface, the following methods can be very effective. For example, if you run the 3D game in the user space, you can have more chance to touch the graphic driver in the kernel. For example, you can run the benchmark program in the user space, such as the Xbench or the GFX bench. And also you can get this kind of normal data generation. Also, here are some tricks to how to generate enough model data to fuzz and keep the whole system always working in our fuzzing practice. For example, the left part is try to reboot the kernel, reboot the whole system from kernel. Because in most cases, the kernel is active, but the user mode application is hung, and there will be no data is generated. So in this condition, we will try to reboot the kernel from reboot the whole system from kernel. Okay.
I will introduce some attack service on Apple graphic kernel expectations. Graphic expectations contain MD series and Intel series. For each series, there are also many different expectation attempts for different modules. This is our accelerator class diagram with AMD Random X4000 expectation. We can see that there are also many different kinds of implementation even in one Java. And the red ones are the real implementation classes worked in my Mac Pro. Usually, the common method to reverse attack service for expectation can be the following. First, we can list all the connection types and their corresponding out service, and then reverse all the external methods for each service. Then we can got those interfaces which can be touched from user space. Actually, we have introduced an automatic method in lldb conference this year. Here we list some hidden attack service, including interfaces which are protected by filter drivers, interfaces whose arguments are controlled by the shared memory, and interfaces which cannot be directly touched by user space processes, but can be accessed by some special ones. Due to the first one had been introduced by previous topic, we now introduce the left two. First is interfaces whose arguments can be controlled by shared memory. We know that we can use our connect map memory 64 to map user space, hardware, or shared memory into kernel. In the kernel, the response MIG method is I'll connect map memory into task. Then it will call map client memory 64 function. And this function will eventually call the client memory for time function implement in the kernel extension. Here, take our accelerator family extension as an example. Its client memory for time function will do different memory operations according to the types. We can see that if memory type is 0, it will create our buffer memory descriptor object and return it to caller. Its caller will use it to create mapping into the kernel task and return this mapping to the MIG method. Finally, this method will return the mapping address and size to user space. And in kernel extensions, it can also use the get-based no company function or no copy function to get the virtual address of the beginning of the mapping buffer. So we can control this buffer data from user space. Next, we will search where this shared buffer is used. From the right finger, we can see that the process sideband buffer function in the our accelerator context2 class use it. It will copy the data from shared memory offset 16 to end into our command stream info object within with while close, and then call the process sideband token function and take the command stream info object and its argument. Here we can see this function use command info offset 32 data and index to call the process functions. And all these functions arguments are our command stream info object and mentioned before. Another important thing is that there are total 33 token processes method and 33 discard method in the display table. So for these functions, I think it will be enough for us to find a bug. Here is the pattern for this kind of hidden attack service. Functions refer to the shared memory data and copy them into another object, and use this object and argument to call the other dispatch functions. Therefore, these dispatch functions can be our first target. For this kind of hidden interfaces, we should figure out the data structure of the argument objects first, and then set up the probe and the critical functions. For example, here is process sideband buffer function. Then we can control the probe bits to mutate and test if there are any bugs triggered. Besides that, there are also many interfaces which can not be touched directly by user space processes, but can be accessed by Windows Server, Safari, or other special processes. And the reason why I study these kind of functions is that normally most of security researchers are mainly focused on those interfaces which impose directly to user space. So I think there might be some bug signal here. For example, the right finger is the code snippet of our frame buffer new user client function. It has 3 connection types. We can connect, shared, and diagnose user client in user space except the server type. However, there are also many external methods for this connection type, so it will be a good place to research. Actually, there are lots of this kind of user client. We can simply use our service open function to test them. Or reverse the sandbox profile of Windows Server or Safari process to get this kind of potential file targets. This is the first methodology for this kind of interfaces. We can find them similar with passive files, which set probe in the isOut connect method function, or research the arguments data structure first and the fuzz each function separately. You know, lldb fuzzer does not need tramline, so theoretically you can fuzz any interfaces freely. Now I will demo how lldb fuzzer works. First, it will connect the remote target using KDP and load debugging script. Here are some commands we added for Fuzz. And we set the probe first and use breaklist to check it if it is successful. And we can set the mutation configuration. Here says the max and min bits is 1, and you set mutation config to show the configuration. This is enable the debug mode. Now we can continue the process and to see if any bug triggered. This is the origin data. This is the mutation information. This is the mutation bits. These are the register information in the fuzz place. Then we can continue the process and to see if any bug triggered. Actually, we write a controller in order to fuzz automatically. Here is an example to find the process sideband function. Okay, that's all. This is an example for one crash we got before, which is an access wallet. Here we list the crashes code dump we got. Now I will introduce the bugs we have disclosed. This vulnerability is found in MD reading X 4000 driver, and the vulnerable function is MD accelerator resources in initialized method. MD accelerator resources class is used to process the graphic accelerator resources information for 3D rendering. This vulnerability can be triggered from user space by MD accelerator service. And the external method selector is 0, whose function name is as new resources. In this bug, the register of RX in the place A is the address of the buffer which created from our malloc function. R15 register is in the place B is pointing to the structure input buffer we mentioned before, which can be controlled by user mode. And the ECX register is equal to R15 plus 0xF8, which point to a value offset 62 dword from structure input. From place C and place F, we can see that it actually used to control the total copy time from structure input buffer content to our malloc buffer. And from the place D and place E, we can see that RDX register is used to control the copy size for each copy. Place G is the copy operation which copy data from structure input to our malloc buffer. So obviously, RCX value is got from user space in place B and has not any checks. Therefore, an out boundary read will be happen if it is a big value. Here is another OB bug found in this function. Actually, this function accepts a structure input buffer whose size is 2424. So if any one bit is not checked properly, it may be resulting vulnerability. This is the pseudocode snap of initialized function. In the place A, we can see that it calls our accelerator resources to initialize function with structure input and structure input side and arguments, and set the offset 34-bit to the 6-bit of member 21 vulnerable in place B. Then in place C, the 6 bit of member 21 was moved left 6 bits and used an offset for an our malloc buffer. We can see that for this value, it has no checks and directly use the space value, so it can be resolved in an OOB read. This is a double-free bug from the process stretch test-to-test function, which belongs to MD-SIGL context class, which is the derived class of our accelerator context 2. This function can be accessed using the MD-SIGL context user class with selected 2 functions, submit data buffers. This is a pseudo code snap of processes stretch test-to-test function. We can see that if V15 equal to 0x@C00 in place A, the resources offset 8 and the resources offset 12 are both get from our accelerator's shared 2 with shared memory offset 24 and 28 values and index. And last, if the member 2 resources offset 8 is not equal to 10, this function will release resources offset 12 and offset 8 from our accelerator shared to object in place B. However, if we set the shared memory offset 24 and 28 with the same value, it will release the same resources twice in place B. As mentioned before, this shared memory can be controlled from user space. Therefore, it will be a double-free bug. This is another double-free bug found in discard stretch to test function. The root codes are similar with the last one, so we will not explain it again. This bug is occurred in MD accelerator resources and XOR bits flag function, which can be accessed with selector 262. This is a pseudo code snapped for syzkaller. And we can see that it calls an AND XOR bit flag function with structure input data and its args. Similar, the structure input here is also the buffer we input from user space. This is assembly code snap of AND XOR bit flag function. We found that in place A, R12D register is assigned with the structure input data and move it to RDX register in place C. In place B, RAX is equal to R15 plus 0x1C8, which actually point to a buffer start address. In place D, it directly uses RAX plus RDX to read the buffer content. Therefore, it will be an out-of-boundary read bug. This bug is found in Intel accelerator driver, and the vulnerable function is Intel accelerator new GTT function. This function can be accessed during connecting the user client with type 6. This is the pseudo code snap of new GTT function. We can see that it uses lock4 GPU access function to get the accelerator system memory address and use it to V8 in the place A. And in place B, memory copy function use V8 and the destination addresses for contains copy. However, the v@ value is not always valid. Here it shows it can be 0. However, it can be other values which we are not mentioned here. Next, we will introduce a methodology to implement a debugger for hacking into SH. Actually, nearly all open source networking expectations are not support KDP protocol, so it's necessary to implement a kernel debugger for hacking to SH in order to apply our Fuzz method. Here is some open source network drivers and their adaptive network card module. Kernel debugger is working in polling mode of networking, and Apple API document described, we should override the following functions in order to support our KDP protocol. The third one is to enable the polling mode. The second one is called by interface poller thread to retrieve input package from the driver. The third and the fourth ones are the debugger controller. And the last two functions are used to be called by the debugger client to pull incoming package or set outbound package after a debugger client is attached. After reversing the exit driver which has already explored KDP protocol, such as Apple BCM Ethernet, we got the following workflow. Firstly, we should initialize a kernel debugger object and attach it. Secondly, enable the polling mode and implement the pull input package function. Thirdly, override the debugger controller and implement a pair of most important functions for kernel debugging. Here is the implementation for the first step in Apple BCM Ethernet driver. When service starts, it will use start getIt function to attach the debugger client. Here is the implementation of pull input package function. We can see that it is actually implemented by receive package function. After research, we found the receive package and service RX interrupt functions are all implemented by this function. So their code logicals are nearly the same. Luckily, the RX interrupt functions has been implemented in many open source drivers, such as RTL series and Intel Master series. So we can refer to them to implement the polling input package functions and receive package functions. Here is the main logical of receive package function. When find the receive interrupt, it will retrieve the packet and check if it is valid. If yes, this function will copy and replace the packet into a new buffer object. By the way, it's up to system here whether to copy or replace according to whichever is more time efficient. If replace, it should update the package physical address first. Then function will check it. Then function will check if this package is the last one. If not, append it to message and continue to receive the other packages. If yes, this function will check the message, checks them, encode them with VLAN tag and update the message length. And last, it will check if this message is a KDP package. If yes, increase the network stack and reset the receive register. If no, just do the last step. Here is the implementation for send package function in Apple BCM function. It firstly allocates a package with a data buffer and move the send package info to it and update its length. Then calling the transmit package to send the package. And last, calling the transmit kick function to update the related status register. And reference to the API document of networking family driver. The set package and output start function should be with the same ability. They all use to transmit the packets. So we can refer to output start about the implementation of send package function. Here is the main logical to implement the send package function. You know, set package is active action. System will directly call the transmit handler to send the replay for debug message. After goes then buffer, this function will first check how many segments should be divided into, and then determine which checksum operations should be performed in hardware. After that, it should prepare the header and command bit for each segment and fill them with data. And last, update the polling bits in register and waiting for output thread to decode them. Here are the references if you want to implement a debugger driver based on open source networking drivers. Now, give the conclusion. We introduce the architecture of lldb debugger and show our debugger Fuzz implementation and usage. Also, we introduce two kinds of hidden interfaces in graphic drivers and show how to fuzz them. Next, we introduce some bugs we have found. Last, we introduce the methodology to implement a debugger based on open source network driver. If you have any questions, just email us. Actually, we have some other bugs which have not fixed yet. You can follow us for details. That's all.